Let us talk about this problem. We are given an odd sized matrix and every row is sorted in increasing order and all the elements of this matrix are distinct. See, I have put these conditions to keep the question simple so that you can focus mainly on the logic. We can relax these conditions and still solve the problem using the same logic. Let's understand the problem with this example. We have 3 cross 3 matrix, total odd number of elements. What is median? See, when you have some elements and you want to find out their median, what you do is you consider those all elements in sorted order, you find the middle element. And if there are odd elements, then always there will be one middle element. And if there are even elements, then there will be two middle elements. And there can be multiple definitions of median. You can find the average of 2, you can return the first one or second one. The most common is average of 2. Here we are considering odd sized matrix. So we just have a middle element and we can return that middle element. So we have 9 elements, and if I write these 9 elements in sorted order, I'll have 1, 5, 10, 15, 20, 25, 30, 35, 40. And you can notice that every row is sorted in increasing order, right? There's no order among the columns, but rows are sorted in increasing order. If you consider this sorted sequence, you can notice that 20 is the middle element. That's why our output is 20. Now let's see this example. We have again an odd size matrix of size 3 cross 5, which means 15 elements. All the rows are sorted in increasing order. All the elements are distinct. If I write all the elements in sorted order, I again get this sequence. And if I take the middle element, I get the middle element as 8. So for this matrix, our output should be 8. Now please pause this video and try to think of a logic that takes a matrix and returns the median. Let us first talk about a naive solution to solve the problem. The idea is to consider the matrix elements and put them in an auxiliary array, right? So we simply traverse this matrix row by row and put all the elements in an array, right? Once we have put all the elements in an array, we sort the array. And after you sort the array, you can simply return the middle element. Now what is the time complexity of the solution? See, this step is going to take big O of R C time, if R is the number of rows and C is the number of columns. The second step is going to take big O of R into C log R into C, because we are sorting the 2D array. The third step is big O of one step. So this is the time complexity of individual step, and if you take the overall time complexity, it's going to be the highest order term, which is big O of RC log RC. That's the overall time complexity. We can optimize it. See, this second and third steps, they can be optimized. We can find median of an array in linear time also. There exists an algorithm, in fact a quick select algorithm, which we have discussed in the quick sort track. That algorithm takes big O of RC time on average. Although worst case it's big O of RC into log RC, but on average it takes big O of R into C time. So overall time complexity can be optimized to big O of RC. The solution that we just discussed does not use the fact that individual rows are sorted. Here we are going to discuss a solution which uses this fact and might work better than the previous solution. The time complexity of the solution that we are going to discuss is big O of R into log of max minus min multiplied by log of C. R is the number of rows, C is the number of columns. Max and min are maximum and minimum values respectively in the matrix. So please pause this video and try to think of a solution that works in this time. And to give you a hint about the solution, we are going to use binary search. Before we talk about this efficient solution, let's quickly compare the time complexities to understand why are we calling it efficient. See, the time complexity of the previous solution was big O of R into C. And the time complexity that we have here is big O of R into this log and log. See, log is definitely better. And how better it is? See, max and min, even if they have a difference of maximum integer value, which is 2 raised to the power 32, this log of base 2 and 2 raised to the power 32 is going to be only 32, right? It's only going to be 32. And C is also an integer value, number of columns, then also, this is also going to be 32 at most, right? If we consider 32-bit integers. So it's going to be 32 into 32, and here we have a value C. So if we have number of columns more than this range, right, this maximum value, and probably these ranges are smaller, then this solution is going to work better. And if you consider large inputs, large size matrix, then it is definitely better. Large size matrix and small ranges. Now please pause this video again and try to think of the solution. Here is implementation of the efficient approach. What are we doing here? We are first finding the minimum element in the matrix and then maximum element. See, the minimum element will be one of these three elements in this matrix, and maximum will be one of these three elements, right? Because every row is sorted in increasing order. So what we do is we initialize the minimum as this and we initialize the maximum as this element. Now we run a loop from the second row to last row and we compare first element with the current minimum and last element with the current maximum, right? And if the element is greater than maximum, then we update the maximum, and if the element is smaller than minimum, then we update the minimum. So this way we are able to find out minimum and maximum elements in big O of R time. We also find the position of median element. See, we have an odd sized matrix, for example this 3 cross 5 matrix, so there will be 15 elements, and what will be the position? It will be 8. And how did we compute it? 3 into 5 plus 1 by 2, right? If you have 5 into 5, it is going to be 5 into 5 plus 1 by 2. So we get the median position as 8 in this example, right? So we know that the median element is going to be 8th position in sorted matrix, right? There are going to be 7 elements smaller than it, and total 8 elements is smaller than or equal to this, right? If we have repeated elements also, then there are total 8 elements smaller than or equal to it, and that's what we are going to count for every element that we consider it as a median, and that's how we are going to decide whether we need to go to the left half of the range or right half of the range. Now what we are going to do is we are going to do a binary search in this range from min to max. So min for this matrix is 1 and max is 40. We find the mid value, right? To do the binary search, mid turns out to be 1 plus 41 divided by 2 floor division 20. Now we find out what is the position of 20. How many elements are smaller than or equal to 20? And how do we do this efficiently? See, individual rows are sorted, so we can do binary search for this. And C++ has this function upper bound which gives you the index of first greater element, right? So for 20 we search index of first greater element in every row. We search in this row. See, we are running a loop for every row, right? And we are calling upper bound, and whatever upper bound returns, we are subtracting that value from mi, right? And that way we get the position or index of the first greater element. Let's understand with this example. So when you search for 20 in this row, you are going to get this index, right? Index of first greater element. So we get the index as 0, 1, 2, 3, right? This is the position, this is the count of elements also smaller than or equal to 20, right? We have 3 elements. Now we search 20 here, and upper bound returns the index as last index plus 1, right? So we get the index as 0, 1, 2, 3, 4. Right, 4 is the last index, and we are going to get 5 because 20 is greater than every element, right? So see, upper bound does not return you index, it returns you iterator, and we are returning the subtracting the first element address from the iterator to get the index, right? So we get the value 5 here, and again 20 is greater than all of these, so we are going to get the value 5 again. So position of 20 is 13. We found the mid element as 20 and we found the position of mid element as 13. And the position that we are looking for is 8, and we have got 13 here, which means 20 is greater than median. So what we need to do is we need to search in left half. To search in left half, we change the max to mid. See, normal binary search, we change the max or right side to mid minus 1, right? Here we are not changing it to mid minus 1, we are changing it to mid. See, we are changing min to mid plus 1, but we are changing max to mid. There is a reason behind it, I will shortly explain. Why are we not doing mid minus 1? Why are we doing mid? So we get the we update the max as 20, right? Update the max as mid. Now we again compute the mid. We get the mid as 10 this time, and now we find the position of 10. Where does 10 stand in this matrix? And to do that, again we call upper bound for every row, right? So we get 2 here, right? And we get 5 here. 2 plus 5, 7, and we get 0 here because all the elements are greater. So 7 is the position. Now the 7 is smaller than the desired position or median position, right? So what are we going to do now? We are going to search in the right half. For that we are going to change our min to 10 plus 1, 11. Now we have 11 and 20. We again find the mid. mid turns out to be 15. We find the position of mid, position turns out to be 10, and this position is greater than the desired position 8. So we again go to the left half. To go to the left half, we update the max. Now we again get the mid, right? And we get the position of mid as 9, and we again do search from mid to max. We get the mid as 12. See, in this iteration, we got the desired position 8, but 12 element is not present itself in the matrix, right? That's why we were doing max to mid in those cases when mid turns out to be greater than median mid, right? We are not doing it mid minus 1. And our condition is also interesting here. We are running a loop while min is smaller than max. See, you could implement it other way also. You could do this way, that min equal to mid and max equal to mid minus 1. We just need to ensure that one of them is not updated, right? And we stop this loop when they both become the same, right? Here you got the desired position 8, but your mid is 12, which is not present in the matrix, right? Because we are simply doing divide of to min plus max. We're not checking whether this element is present in the matrix or not. For that purpose, we bring those elements closer. We don't stop when we get the desired position. To get them closer, we now have min as 11 and max as 12. They are not same, and our condition says that don't stop the loop. Now what we are going to do is we are again going to compute the mid. Mid turns out to be 11 this time, and we find the position again as 8, right? And in case of equal, again we do mid equal to max equal to mid. So max becomes 11. Now min and max become same. So we stop here. We found the desired element and we found the position also 8, right? So that's where we stop, and we return our answer as min. See, after this loop is over, both min and max would be same. So you can either return min or you can return max. So in the overall approach, what are we doing? We are finding the middle element of min and max. Then we are checking if the position of the middle element, we find its position doing binary search in individual rows. And if this position is smaller than median position, the desired position, then we go to the right half. And if it is greater or equal, then we go to the left half. And we go to mid, right, to ensure that min and max, they become same when the loop gets over. And after the loop gets over, we return the min element. Let's now quickly see the time complexity. The time complexity of this part, as we've discussed, is theta r, right? And this part is going to run, this loop is going to run big O of log of max minus min, right? We are doing binary search in this range, max minus min, right? And inside this loop, we are doing binary search in every row. So there's going to be a loop for every row. So that's why we multiply it with r. And in every row, we are doing binary search, right? And every row has size, column, right? Number of columns. So then we do binary search in every column. That's why we get this time complexity. And this term is higher than this term, so we ignore the lower order term, and our overall time complexity becomes this.